I'm going to be talking about computer vision, but in the context of sort of the new wave, which is deep learning. But let me start with some big picture context. Okay. I want to start with this argument from Hans Moravec's book, which goes back to the 1990s. And Hans Moravec tried to compare the computing power of the human brain with digital computers. And he makes some assumptions. He makes some assumptions about what neurons are as computing devices and so forth. And you can argue a bit with these assumptions, but it gives you a good first order analysis. And what he says is that assuming Moore's law, he wrote this book in the 1990s, we should have human level computing power in 2025. Or if you have a cluster of 100 nodes, and this is very much what we have today, then you have that computing power in 2015. And he produced this plot, and it goes back to the 1960s and so on and so forth. And on this plot, basically where we are now is that time when computing power of machines is the same as human brains if you are willing to use enough GPUs and so forth. So I would like to argue that this is the first thing we should keep in mind. When people in our field were trying to make AI or computer vision happen back in the 60s and 70s, they were really operating in as heroes. They were heroes, but they were operating in a setting where they were doomed to fail. Now we are lucky. We have that computing power. When we had computers which were a million times slower, you were forced to make gross simplifying assumptions. And that's sort of why we had all the symbolic AI of the 70s. You had to make those grossly simplifying assumptions. We don't have to do that anymore. And now it's up to our ingenuity. If we have the right ideas, we can make AI happen. So at this time, how should we think about AI? I think we really should think about the whole problem, and the whole problem, of course, has these different aspects. Vision, or vision I'm taking in as a Visionchauvinists to stand for all of perception. Motor control, which motor control robotics, broadly planning, and then, of course, language and semantic reasoning, so higher level vision, higher level everything. So all of these are, of course, coupled together in the brain, and I think it's very helpful to think about the phylogeny of intelligence. How did intelligence come by in biology? And it goes back to about 500 million years ago. The Cambrian period led to the emergence of a wide variety of animal life, and these animals could move about and they could see. And it's very important to think of this, that vision provides benefits together when it's accompanied by the ability to move. If a plant, imagine these trees, tall trees, if they had vision, perhaps they might discuss the environment with other fellow trees, but it would confer no evolutionary advantage. Whereas when you can move around, you can go find food in various places and so forth. And that's what locomotion does, accompanied by vision. And that clearly gave. There are people in biologists who have written books which argue that, in fact, the Cambrian explosion was due to the development of vision, because it enabled a whole set of new niches to come by. Okay, if this coupling between vision and locomotion, Gibson made a big deal of it, but there are some very cute examples in biology. So there is this animal called the sea squirt, which for quite a bit of its life cycle, it's mobile, but then there is this stage where it becomes like a plant. It gets stuck on one rock and that's it. And at that stage, it has no value for its vision, right? Because it can't move about, so it can't get any food as a result. So what it does is that, in fact, it digests its entire nervous system. It has no value. The brain, for humans, it uses up 30% of energy. And if you don't get any value out of it, then you may as well get rid of that 30% of extra metabolic cost. So moving right along, when we get to 5 million years ago, we have sort of the development of the hominid line. In the primates, we have development of humans and so forth. And the interesting thing here is the development of the hand. And generally, the evidence suggests that the development of the hand precedes the development of the brain. If you look at the fossil record, you sort of have the species with 1,000 cc brains and 1,200 cc brains and so on and so forth. And in the sequence, the hand development gives you that ability to do things which then gives you an advantage of having a greater brain. And there was a debate going back to the classic times of the Greeks. In fact, this fellow Anaxagoras, and I really have this quote in Greek, which I've been assured by my Greek students is accurate. It's that it is because of his being armed with hands that man is the most intelligent animal. So the hand comes first and then the brain. Someone like Aristotle had it wrong, who argued the other way around, that it was that man is intelligent, therefore he can make use of his hands. So then, of course, 100,000 years ago, we have language, and there are a variety of theories about language, and I'm not going to get into that because that's not the main purpose of my talk. But the big picture is that if you think about evolution of intelligence, we have these stages. Vision and locomotion, roughly 500 million years ago. Manipulation, like 5 million. Language, like 100,000. And successes in AI seem to follow the same order. So in some sense, vision is now has made a lot of progress, and so has locomotion. Certainly, if you are willing to use wheels, and if you put the two together, well, what do you get? You get self-driving cars. So, to my mind, it is just obvious if you look at the phylogenetic progression that self-driving cars was bound to be the first big success in AI. Manipulation, in my view, is there's been a lot of work in robotics, but there is a fundamental problem. The fundamental problem is that robot hands are nowhere close to human hands in terms of the flexibility, the sensory capability, etc., etc. So I think that when we talk about robots in the home, there is going to be, as far as I see, there is no hardware limitation which is blocking us on the vision and locomotion part of things. But as far as the hands that can do everything that the human hands can do, I don't think we are there yet. Our cameras are as good as eyes, but our hands are not as good as, robot hands are not as good as human hands. Okay, with this general philosophy, let's turn to, I'll return to this later in the talk, but right now let me stay at the big picture, get to vision. So what do we know in vision? We know that we are at a very great successful point. And I picked this slide. This is from work done by Microsoft Research Asia people, and this is results from nearly a year ago. And this is amazing. I mean, these are sort of the detections of various people and dining tables and chairs and knives and so on and so forth. And this, if we had asked 5 years ago, anyone in computer vision working in object recognition, would we be able to get there in 5 years? Say in 2011, if you had asked us to bet on this, I don't think any of us would have bet that we would be at this point in 2016 or 2015. So this is quite a remarkable success story, and let's try to unpack this a bit. What was responsible for this success? So I think this is actually a story of biologically inspired intelligence, which has been a minority strand in the computer vision community, but nevertheless it has existed throughout the 50 years or so of computer vision. So if you go back to Hubel and Wiesel back in the 1960s or so, they first on cat and then on monkey, they discovered these orientation selective cells. And there were edge selective cells and bar selective cells and so on and so forth. And this is connected to people's use of edge detection as an early stage in vision, but you could argue that that might have been motivated by simply compression kind of ideas. And in fact, compression had to be done in those days because we couldn't afford to keep the pixels around. We had to get rid of them as quickly as possible, given the computing power of the 60s. Now, there were people who took the Hubel and Wiesel insights into neuroscience, the stages of simple cells which are followed by complex cells, where complex cells are doing pooling over slightly larger areas so that there is a little bit of shift invariance built in, and then you just keep stacking this architecture with so-called hyper complex cells and so forth. So this design of alternating layers, which are sort of like which are like convolutional stages followed by some pooling stages, and repeat that process, was in a way, it was kind of the received wisdom in neuroscience, and people in the neural network community, such as Fukushima, sort of formalized this and built on it. The so-called the Neocon architecture, their publication in 79 and 80, which sort of laid this out fully. It's a beautiful example of an architecture inspired by biology, which in fact he used it for digit recognition. But there was one thing which he did. He was much too slavish to biology, so therefore he wanted to have a learning method for figuring out the weights of this neural network with some variation on Hebbian learning. Now in the 80s, backpropagation comes along. So that's work from the connectionist group of people like Hinton and Rumelhart and so forth. And initially, they made progress by ignoring some of the details of biology. So backpropagation there's an article by Francis Crick from the 80s on why backpropagation is really not at all biologically plausible. But people said, fine, doesn't matter. Let's see if we can do something interesting with it. And once you take backpropagation as a learning rule and you combine it with the neocognitron, you get convolutional neural nets of Jan LeCun et al. And if you look at LeCun's 89 paper, it has the neocognitron architecture together with this insight that we can have an error function and differentiate it and use that to figure out how the weight should change. So all this was there in the 80s, in the late 80s. And then in the 90s and 2000s, somehow it fell into disrepute. And why? It's not because neural networks ceased to be effective. There were very impressive applications going back into the mid-90s, for example, on face detection from Takeo Kanade's group and from Poggio's group and so forth. It was just that neural networks are sort of delicate beasts and you have to figure out how to use them. Whereas certain other techniques such as support vector machines were much easier to manage. And my way of judging this is, if I give homework assignments to students at Berkeley and one group is asked to make something work with neural networks and another group has to do linear SVMs, the linear SVM assignment will be done by 99% of the students. And the neural network one, there'll be some people who will be worrying about learning rates and some people will be worrying about how many layers and so on and so forth. So that's why neural networks fell into disrepair. It's not that they didn't work, it's that there were alternative techniques which worked equally well, but they were much cleaner mathematically and much easier to handle. Now things changed, and they changed sort of in the 2000s. Deep learning, which is this area relabeled, was somehow not so, was a minority interest, and in the early 2010s, what you have is that the combination of the old architectures with the fact that you have GPUs and that you have a large amounts of training data, such as ImageNet. You put these together, and that's what led to Krzyzewski, Sutskever, and Hinton's major success. And I was responsible for it in the following sense, that I had this conversation with Hinton where he said, why don't you vision people take us seriously in deep learning? And my argument was, well, until you show us results on some data sets that we care about, we won't be impressed. And that they did start to work on ImageNet, and of course that's one of the. I would say it would have happened anyway, but anyway, that's my little role in trying to encourage this process. So initially we were skeptical. I remember myself not believing that these results applied to anything other than just the ImageNet challenge. And what we found was, no, this was not a very specific result. It applied to a wide range of computer vision problems. And then, of course, the creativity of computer vision community was unleashed on a range of problems using neural networks as function approximators. And as they say, all the rest is history. So specifically on the task of detection, which was, you don't just say that in the image there is a horse, you actually must locate the horse with some kind of bounding box. Here I'm highlighting one of the papers from Berkeley in that early era, which showed that you could combine the idea of a neural network as a function approximator with standard computer vision techniques such as bottom-up region proposals, put them together, and then try to find out, say that this region corresponds to a person. And okay, so we had this success that we not only could we do classification at the image level, that somewhere in the image there is a horse, we could in fact localize the horse. There are versions of this. This was RCNN was region CNN, and then there was a faster version and faster version. And again, all this is now very standard stuff, so I won't recap this. The main thing to realize is that the architectures that we have been using have been inspired by a lot of sort of insight into vision, how you put things together. And then there is a separate aspect, which is exactly what neural network do you use. And there, the basic observation seems to be deeper is always better. And if you look at these papers over the years, every time you've gone deeper, it seems like it has resulted in a big gain and improvement. Okay, so I want to just give one example, it's a parochial example from Berkeley work on how one can take this basic building block of a neural network as a function approximator. Actually, it's a convolutional neural network as a function approximator, and sort of use it in creative ways with our vision knowledge of how various architectures should be designed for various tasks. So the example I'll take up is one of action recognition, where action recognition really requires multiple cues. It's the appearance of the person who's the actor, as well as other objects that might be involved, interactions with other people, and so forth. And the question is, how do we construct a learning architecture to capture all these? So, okay, before I talk about this equation, let me jump to these pictures which illustrate what's going on. So here in these images, you see every row corresponds to some action category. So the top row is jumping, the second row is phoning, playing a musical instrument, reading, riding a bike, and so on. In each case, the actor is in red. So the red rectangle corresponds to a person whose action you're trying to label. So in the second row, that red corresponds to a person who happens to be phoning. Then in green, what you have is some auxiliary window, and this auxiliary window has the most relevant part. Think of it as a attention to a relevant part. So in the case of phoning, the relevant part is the face and hand combination in this era of cell phones and so on. So there is information in the red box, and then there is information in the green box. Now the magic here is that in the old days we would have said, so if you look at the third row, that green box happens to be usually this musical instrument. So we would have sort of hand programmed it. We would have said actions involve objects, so let's detect the object, and then we must use the features computed there as well. The magic of the new style of work is that we actually can have, so now if we look at the slide with the architecture, we have one pathway which is this red pathway and one which is the green pathway. So one corresponds to features computed on the person as a whole, and one on this auxiliary region. And you sort of have this max there on the green pathway, which suggests that in this there are many possible choices of this auxiliary region, and we'll take the one which is most informative. And so in a way, we can do this, and we don't need to hand build what auxiliary region you should use. And sometimes that auxiliary region, I mean, this is formalized by the equation in the previous slide, but this is not so important. The auxiliary region sometimes can be the whole scene, which provides context. Sometimes it could be other people who are performing similar actions. Sometimes it could be the object. And all this is figured out at training time. So this is sort of an illustration of this general philosophy, which is that learning seems to beat hand design of various of these things. And I sort of have come to accept it, because what it does is, of course, it for somebody who spent so many years trying to be clever about using all their vision knowledge, to feel, it almost feels like, are we out of a job? Because is this learning architecture is going to take care of everything? And then I've concluded that this is not quite the case. What we do is, our ingenuity just goes to one higher level, which is that we don't try to design the features, we design the learning architecture. And in that, we use our vision knowledge. And then after that, we let the data speak. So we just have lots and lots of example pairs, xi, comma, yi, and we let the data do that part, and the architecture is where our insights from vision come in. And obviously, the design of this particular architecture is based on the fact that context is useful in recognition. Okay, and well, here are numbers, but the numbers should be good, otherwise the paper would not have been accepted. So, so now let's look at this this image and try to see what do we as humans see here. And the interesting thing is that right now there is quite a lot which is in reach for the computer vision community. So I'm showing you here what I think are collective results and as published in CVPR, ICCV, ECCV, what have you, would enable us to do. We can detect objects, we can mark out the pixels corresponding to the object, we might mark the stick figure, we might take an object, match it to a 3D model, etc., etc. I'm not saying that all this is done yet, but this is where the papers that are being written are. And if today they are at 83%, tomorrow they'll be at 87% and 92% and so on and so forth. So, so of course this should continue, and increasingly, of course, companies are going to take the lead on this because they will have the huge collections of data which will ultimately determine how the best the numbers are. So, so what is left to do? And as an academic researcher, you want to sort of find the aspects of the problem which are sort of interesting, where you can explore things as an academic. So here are some of, I'll pick 3 items here as interesting ideas which we as academics can explore, and this will contribute to better vision results or applications in the future. So feedback architectures, 3D understanding, and then prediction and self-supervised learning. And I'll take up each of these in turn. So let's start with feedback architectures. So go back to the neuroscience insights, right? As I said, the convolutional neural net is Fukushima's Neocon, which is really Hubel-Wiesel multi-layer architecture trained with backprop. Well, we know from biology that this is not it. There is feed-forward connections as well as feedback connections, and these have been known forever. And to me, it's a very interesting thing to pursue in computer vision, that to find tasks where feedback is the key to the solution. And I don't have a general theory here. What we have are various case studies, and I'm going to take you through some examples of that. So, okay, here's a slide which is meant to show that in biology we know of feedback pathways in between. If there's area A connected feed forward to area B, there's a feedback pathway from area B to area A. Okay, so here's a problem which we tackled in this framework, and so think of these as case studies of how feedback helps. So here's the problem. So the problem is pose estimation, and the rightmost column shows the end result. So it's a stick figure where the each of the line segments corresponds to some body segment, and then the joints correspond to body joints like left shoulder, left elbow, left wrist, so on and so forth. So in this setup, the way we are going to do it is we are going to do it iteratively. So the starting point is what's shown in column 1. So column 1 is this initial guess, which is always a person in anatomical position, person standing vertically with arms on the sides and so on. And what the network tries to do is to try to correct the guesses, this guess. So instead of trying to predict the final answer in one go, what it tries to do is, how should I move the various joints such that they become better explainers of the image data? And that's what you see in step 1. So the joints have been moved a little bit. And then in step 2, it tries to correct from the initial condition in step 1 and so forth. And not many iterations are needed. I mean, we should not have too many iterations, because they will introduce way too many delays. And after all, vision is for guiding actions. And if you have huge delays, then you're in trouble, because you cannot wait forever to decide whether what's in front of you is a tiger. You'll be eaten before. So how do we do this? So the general style that we have used here is, so this fits into the framework of recurrent networks, except that we thought that it is much, in fact, can be thought of very simply, and using ideas of feedback and control systems, as in, standard electrical engineering kind of ideas. So the basic setup is that you have an image and you have this initial guess of the of the key point configuration, and what you do is you take those two as input, and then you predict the correction. So the correction here is shown as epsilon t in this diagram, and then the new stick figure is the old stick figure plus this correction. And what the network has to do is to always predict the corrections. So this turns out is an easier problem, because in a way it's like you have a Taylor series expansion. You are around an operating point, and the identity is your previous guess, and then you're trying to do corrections to that. Now, whenever you have a network like this, which just has a couple of rounds of feedback, then of course you can think of it as unrolled into an equivalent purely feed-forward network. So yes, this is equivalent to a purely feed-forward network with certain weights tied, but to me it's more interesting to see it this way, and this gives us insight into the design of architectures for many other problems. And you get this very nice behavior that as the iterations proceed, in the first few iterations the main parts of the body get assigned, so it's like a coarse to fine framework. So initially the head and shoulder somehow turns out to be right very quickly after one iteration, and then the other parts of the body land up correcting themselves in the context of that first part. Okay, and you get decent numbers. Fine. Okay, and here are some. These are results I've shown you already, but here's another example. So I particularly like the second row here. So here's this woman in a yoga pose, and she's totally horizontal, and yet our starting point is a person in a vertical position, and yet as the iterations proceed, the parts of the body sort of line up correctly, and at the end we've got a pretty good result here. And there are, currently some of the leading approaches, what they do is essentially a series of stages. So you just have multiple stages of these kinds of conv, deconv layers, as people call them, and that's in a way equivalent to what our feedback architecture unrolled would be. Okay, there are more examples of the use of feedback. So for me, this is a philosophical thing. I want to now try to solve various vision problems in a feedback kind of paradigm. So here's one, which is something we published last year, and this is on image iterative instance segmentation. So the goal is instance segmentation. So we want to find masks corresponding to each of these people. So now in the middle column are results from our previous algorithm, and what they have is this kind of funny result, which is that here's this person who's been segmented out, and this person appears to have two heads. Now, why does this kind of a result arise? If you look at the local receptive field structure, it all makes sense, right? Because locally all these are parts which are person-like. Now, once you have a sort of global context that this is a person and this is roughly where the person is arranged, then you know that you can't have two heads. So in the context of your initial segmentation, it should become much easier to figure out that some of this part is stuff is extraneous and should not be there. And so we have an architecture which uses feedback exactly for this, and indeed we get results which show that improvement. So what's the architecture? So you start with a basic feed-forward prediction architecture for instance segmentation, which tries to mark out the pixels corresponding to a single person. And then what you do is that you have that previous guess and the raw image, and now you try to predict a refinement, and then you continue. And so it's the same philosophy as we used for the stick figure case, and it gives clear benefits. And again, I'm going to skip more details on this. So my prediction here is that we'll find. We'll continue to obviously see just more and more exploitation of convolutional neural nets, but I think we'll also see increasingly applications where these feedback architectures are being exploited, and they enable us to provide sort of context and top-down information in a fairly natural way. And okay, next topic that I want to touch on is 3D understanding. So if you look at a scene like this, we see this person, but obviously we see more than just what we see there, right? We see something like this. We imagine that there's this person who extends, and then the chair extends, and so forth. So psychologists have a term for this. They call this amodal completion. Kanitsa wrote a lot about this. And this amodal completion, which is important for robotics, right? Because you need to, if you are going to move around in the world, you want to reason about the objects that are there, even the visible parts as well as the invisible parts. If you want to walk around the chair, you need to know the full extent of the chair. So how do we achieve this goal? So now it's helpful to note that, in fact, knowing the amodal completion is helpful for geometry. So essentially, the kinds of cues that we are using now, these learning cues, need to be combined with the geometry tradition. So there is something we know for a long time, which is, that if you have an object on a ground plane, then where it is located vertically on the image plane is related to how far away the object is. The closer the object is to the horizon, that means the further away it is, and is simple geometry that you can do. This was known to Euclid more than 2,000 years ago. And so once you can do this amodal completion, so you can figure out where the objects extend to, we can in fact reason about their placement in 3D as well as their 3D sizes, and it can be done sort of nicely in a paper which we published now, I guess, at ICCB 2015. Here's another example of sort of amodal reasoning. So here we have this horse. Well, actually, if you look at the instance segmentation done in the straightforward way, we appear to have two pieces of something, right? But we don't see that. We perceive that this is really one solid horse, right? That's amodal completion, because we see the person in front and we infer this occlusion pattern and so forth. So how do we do this? So this is again an example where you want to do this implicit 3D reasoning about objects in a 3D world, and again, I'm not going to go into the algorithm there, but it was published at ECCB. So now I'll get a bit more general. So we have two great traditions in computer vision. There is roughly the recognition tradition, in which now I think all of sort of understanding, recognition, segmentation, they've all got merged into that one tradition. And this is where learning really applies. And then there's this other great tradition in computer vision, which is that of geometry. And there are, the visual system is a great geometer. After all, we make inferences about the 3D world, and we operate in a 3D world, and we need to have that. And how do we, so we, in the early years, what we have seen is that these two traditions are sort of kind of living in an uneasy way with respect to each other. We don't know how to sort of combine them. So I think that one of the interesting areas for us right now, and continuing on for the next couple of years, is really to bring these two traditions together, because the geometric tradition has a certain strength, there's a certain clarity, and all those facts of Euclidean geometry we should not ignore. We should bring them in or incorporate them into our architectures. How we make this marriage happen, so how do we redo all of shape from X, etc., etc. I think this is what's being worked out right now and over the next few years. So here's an example problem, which is that of abstracting out shapes. So this is a very classic tradition. This is in computer vision, this is the generalized cylinder tradition. So when I was a PhD student more than 30 years ago, this is what my advisor Tom Binford wanted me to work on, to describe objects with as combinations of generalized cylinders. Okay, can we do this in the neural network world? So what we have to do is to somehow explain objects as a combination of volumetric primitives, right? And the paper is going back to the 70s and 80s, and Rod Brooks wrote a thesis on this, and a lot of work has been done in this, but with handcrafted rules. So instead we can imagine sort of, throw a neural network at it. So the input, so what we are trying to do is that this network is trying to predict these volumetric primitives. So it's trying to predict each of these cuboids, and that cuboid has some parameters of its shape as well as its rotation and translation. And then, of course, we want to have a probability that this primitive is actually used. And it turns out that this machinery, which it leads to, what we need is always a differentiable loss function. So that's in the new era, as soon as you can construct a loss function which is differentiable, you are in business, because then you take the derivatives and now you know how to change the weights of the network, and you're golden. And for some magical reason, even though you're doing stochastic gradient descent and you're going to be stuck in a local minima, there are plenty of good local minima, and so we are all happy. We have learned to accept this. A few people are still bothered by it, but I think most people just carry on. Okay, so the setup here would be, there is a loss that each of these must be included in the other, and I'm skipping the details, but it works remarkably well, and you can see some of the results here, where essentially after this training stage, you can feed it any new object like any chair, and then it will pass it into these. It will make that chair out of those cuboids, and this is now getting at semantics, right? Because this is essentially enabling us to get the right notion of semantic part. So okay, so you see examples of chairs, these animals. So in fact, you can have this general model for all quadrupeds, which get decomposed into a head and torso and legs for aeroplanes and so on and so forth. So I have not shown these results to Tom Binford, but I would like to know what he would say. And then, of course, you can do graphicsy things here. Okay, I'll take the liberty to show another sort of brief result along this line, which is trying to marry geometric reasoning with this learning-based reasoning. And so think of your classic space carving kind of thing. So you have an object and you have multiple views of it from different directions, and you're trying to construct the 3D model. And we have earlier papers on this, and in the neural network era in some kind of a hybrid way. Okay, so what do we do if you are a true neural network junkie? You try to construct a differentiable loss function. So what do we want to do? At the core, the challenge is there is some 3D shape which we are guessing. There is some 2D projection which we get to measure, and we are trying to ask the question, is the 3D shape consistent with the 2D observation? So if we can construct a loss for that, then we can imagine differentiating that loss function and using that to tweak the weights of the neural network. So how might this work? Again, just a sketch of the idea. So essentially there's a ray which is coming, and this ray from the camera, and then it's going to get stopped at some point because there's a voxel which is occupied. But if there's a voxel which is occupied, there must be previous voxels which are not occupied. So you sort of have to consider this conjunction event, empty, 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 and then suddenly it's filled. Now the emptiness is what you're now trying to predict for every voxel, and now that's, you can do some little bit of mumbo jumbo, and it's fairly, the intuition is obvious from what I suggested in the last slide. And but the magic is, okay, it's all going to turn out to be some differentiable function from which you ultimately get at you can tweak the weights of the network, and it does nice things. So that's about 3D, and this enables us to do reconstruction. Again, I don't claim that this is done yet, but this is sort of the flavor, right? We are trying to combine these two different ways of thinking, geometric thinking as well as recognition, prior knowledge thinking. We sort of have to put stuff into a common language. So basically, either you have to talk, everybody has to talk in English, or everybody has to talk in French. And it looks like we have discovered English for this world. And that English is the language of neural networks and as a function approximators and differentiable loss functions. It's really, that seems to be the language in which we are finding the most success these days. Now, let's move on to where we want to go in the future. And we want to go beyond just characterizing these objects. I mean, that's fine, but that's not, we want to get at grand goals. And to me, if I look at this image, to me, the most interesting question is, will this person put some money in this other person's tip bag? Because when I analyze this, it's clear that this woman is a musician. There is a bag at her feet, and there you can see some dollar bills there. And this guy is looking, and maybe he's a cheapskate. He doesn't want to pull out any money, so then he'll quickly sort of disappear. Or maybe he likes the music and he's trying to decide whether to give her $1 or not, right? That's the kind of thing we want to reason about. This is, of course, one example, but roughly speaking, we want to understand the scene, which means that we want to understand how it's going to evolve. So, big picture, what is this about? I would call this the field of social perception. Okay, so people talk about IQ, right? And IQ is made up of many different components. So maybe we should have VQ, VIQ, visual intelligence quotient, and that has to be broken up into different things. So maybe we are very, very good at labeling patches of pixels with labels of objects, but that's not enough, right? We want to understand the scene, interact with it. And computers today have very low social intelligence. We need to understand the internal state of humans as they interact with each other in the external world. So emotional state, body language, current goals. So yes, the stick figure is a proxy to this. We can start out that way, and that's an example of initial state. Looking at people's faces, you can get at their emotional state. Are they happy, sad, etc.? But of course, it's got to be much more than that. So what is needed is really an understanding of the structure of human behavior. And human behavior is it's goal directed. We are trying to achieve something. So we take certain steps, and those steps make sense in the context of some goal that we are trying to achieve. So an action has a visual signature, that's a movement. But that's just part of it. That's the surface appearance. There is a deeper underlying thing, which is the goal of the person. So we we will have to deal with that. The field of action recognition, in my view, is like about 10 years behind the field of object recognition. And in object recognition, I think we have all the key components. It's now really just engineering and more data and so forth. There might be big discoveries still to come, but mostly it seems like we are there. Whereas in action recognition, I think we are mostly not there. We don't even have the right data sets, at least in the public domain yet. So how should we think about this? So for me, this is how I like to think about it. It's the concept of a mental model. And this was written about by Kenneth Craik in 1943 in this beautiful paragraph, which I urge you all to read. So, if the organism carries a small-scale model of external reality and of its own possible actions within its head, it's able to try out various alternatives, conclude which is the best, react to future situations before they arise, utilize knowledge of past events, etc., etc. So, that is what we want to have. And in fact, Craik died back in the early 40s because of some car accident. But in a way, this can be thought of as a precursor to the development of cognitive science, because cognitive science moved out of pure behaviorism and which didn't want to look inside the black box and didn't want to have models like this, as well as control theory. I would say control theory of Kalman, state space, etc. is really also the same thing. It's just that the control theorists chose to construct a more simple world in which they could construct these models. So they could have x dot equals ax plus bu, y equals cx plus du, and these a and b and c and d were sort of linear, and things were good. So of course now what we have are these nonlinear boxes, right? These neural networks which have multiple layers in them. But okay, replace linear by nonlinear. I think that in a way, with these neural networks, we can construct. I think our goal should be to really build these models, and then we can run them in a forward direction to sort of understand what will happen. But they also tell us how to control, because you know how to change the control input. So this is a very broad, sort of fuzzy research agenda. And I want to, of course, take the moment to bring it back to the big picture, which is that I think once we start talking about mental models, and this is what we have to do, I think, to truly understand action, we are no longer in a nice isolated world of vision by itself. We must, these mental models are the way where vision interacts with motor control, and of course with higher level reasoning as well. So this is a point at which I want to take a break, and I can take questions here, and then I'm going to start off on just some initial steps down this path. Hi, Yash. Yeah. So I have I have a second part. Do you want me? I have a. So how much time do I have total from now? Yeah. Okay. So that's enough. Yeah. I have a sort of a 15 minute segment on the rest. So do you want me to do that now or take questions here? Okay. Okay. Yes, and we have done that. I mean, I think with 3D models, for example, this is a key problem, because we have lots and lots of objects which have been labeled as in 2D, but we don't have 3D models for those. So in this whole world of 3D stuff, often you are forced to start with CAD models, which are kind of clean, but then the images that you generate from them are not so real. So we have, and other people have, such as Leo Gabus's group and so forth, have done work in that style. There is a domain shift problem after that to deal with. The images that come out are way too clean. But I think that over time, this is going to be the way to go. This is going to be part of the answer. It's not the full answer, and there'll be some things I'll say in the second part of my talk on this. At runtime, you just produce one version after the other. So you run the network once, and you get an improved estimate of the pose. Then you feed that in again, and so forth. So it's going to happen just by the dynamics of the network. You run the network. So the network is being run explicitly, say 3 times, and at each time the output of the previous iteration is being used as input. So if you want to think of it in x's and y's, you have as input x comma y sub t, and you predict y sub t plus 1. That's what the network is trained to. The network can be used to approximate any function, but it's more like a structured output problem. You use both of them as input. Yeah, we don't enforce that explicitly. That just comes out in the wash. Yeah, I mean, we don't want. So I think I'll skip the details of that, and since Alyosha is there, you can ask him all the details. Yeah. Fair enough. I mean, I think they're going to reflect. I mean, this is a generic criticism of all learning approaches, right? They capture the regularities in the data, but that's all they capture. So, in a sense, so to me, I don't have any silver bullet, but I think it's a combination of designing architectures and loss functions. It's really about clever loss functions which incorporate more and more stuff, and essentially that loss function has got various things built in, and then rely, and then you pray. I mean, so this is not satisfactory because this is of course totally in the supervised paradigm. I mean, what I've shown so far, but that's a good setup for me for the next part of my talk, and maybe I'll jump in onto that. Okay. Okay, that's good. That's okay. So ready to go on that. So the first part of my talk was really about I think what's the mainstream computer vision community is doing these days, and where at least some strands along which we should be going in the future. Uh, this part of my talk is a lot more speculative, and it's more like case studies rather than fully all everything is settled kind of system. Okay, so I start by reminding you that we must couple vision with motor control and language, and then let's look at the big picture. What has been responsible for recent AI successes? So big computing, big data, right? Because the basic neural network architectures are not so far different from what existed in the late 1980s. But we do have NVIDIA GPUs and data sets with millions of images. And it's more than that. It's really also big annotation and big simulation. So let's take the ones which have captured most of the popular attention, right? What will show up in the Economist is success at Go, or these Atari games and so forth. Okay, what's the characteristic in these cases is that you also have big simulation, right? You have these domains where everything can be simulated perfectly. So it's really all of this together. Now let's compare this to how children learn. So here you have this baby in the crib. What's this baby doing? There are these all of those who have had children can observe kids, and what we see is that initially they just keep babbling, they keep doing motor babbling, they keep trying things, they keep trying to reach to various objects. So first they just reach, then they manage to grasp, they're just experimenting all the time. Alison Gopnik, who is my colleague at Berkeley, she has this book called The Scientist in the Crib. And the whole thesis is that the children are exploring the world, they're conducting experiments, they have hypotheses, they build models as a result. So they're really doing all of this. And they're doing all this in a multimodal way. So when this child reaches out to some object, there is the motor system which is involved, there's the proprioceptive senses, there's vision, there is some sound which is created when the hand bangs against some object. All of this stuff. Okay, that's what the child is doing. Okay, now there is a little bit of supervision, right? So at the top we have this picture where the mother is saying to the child, "Look, there is a zebra." But does the mother find 1,000 examples of zebras from all different viewpoints and so forth, and then say, "Yes, zebra, zebra, yes, zebra, yes, zebra, yes, zebra"? Maybe this happens like for 2 zebras or something. Okay, what's really happening is most of the time what the child is doing is this experimentation. So there is all this process which these slides try to convey, and it's that child, this scientist child, who has learned a lot from self-experimentation, and that child is a very, very smart individual, and that child, you just give them 2 bits, you say that's a zebra, and then bingo, it works. So I think that in the future has to be something like this, and of course this has been realized by people in the neural network community, and they've talked machine learning broadly, and it's generally the label which is used is unsupervised learning. I don't like that label much, because to me unsupervised learning it doesn't give it much structure. It's sort of, at that point you land up with, okay, you model it, and either you're going to do clustering or you're going to land up doing principal component analysis or something like that. What we know, again, we can look at biology and the child development literature, and I've just picked one article out from Smith and Gasser, which essentially tries to summarize what people in this field know, and there is a rich tradition, right? So people like Spelke and Carey and others, and I encourage lots and lots of people in computer vision and machine learning to really look at that literature. And here is a kind of a summary. So one is multimodality. So you do experiments where multiple senses and motor control are involved at the same time. So there is the visual signal, the auditory signal, the motor commands, etc., etc. Incremental, meaning that there are stages of learning. So these arise due to very natural reasons. So for example, in vision, the early stages, the visual input is very blurred. So you sort of because of the way the photoreceptors move and so forth. So in fact, you're getting coarse to fine. The early stages, you're going to have a much lower resolution input, and then you build a system around that, and later on you have fine resolution input. Physical, obviously the child is, there's a real physical world. It's not sort of the brain in a vat, if you will. There's exploration, social interaction. And there are thousands of papers literally in the field from psychologists who have used very clever techniques to understand the behavior of children who at that stage do not have language and cannot be queried in the same way as adults, but yet by techniques such as preferential looking and so forth, you can figure out a lot. So I think that this is what we have to do in the future. I think supervision and annotation of like millions of examples, this is like a drug, right? This is the heroin of our community. We have learned to love this, and of course, today if you are doing a startup, I mean that's what I would say. Okay, use your supervised data. I mean you can hire a suitable number of people and do it. But this is scientifically not at all interesting. I think that scientifically we want to go to the regime which captures some of this process by which children acquire their mental models of the world. And so this is now I think we don't have any coherent general theories for this style of learning. Whereas we have a very coherent theory for supervised learning, right? You have a loss function, you differentiate it, you backprop, you change the weights. We don't have a theory for this style of self-supervised learning or experimental learning or what have you. Okay, so there's a paper we wrote earlier, but let me get into a different style here, where vision and robotics sort of get coupled. So just think about how this business about when you poke at a Coke can or when you poke at this balloon, different things happen, and that's really what's interesting. You might try to say that we can have we try to sort of, how would classical robotics do this? You would have Newtonian physics built in. You would need to know the properties of every object, and you would have to sort of do simulation. On the other hand, we can try to learn from experiments. So the child is not a Newtonian physicist, but sort of a pre-Newtonian physicist. This is the child's experiments. In the child's world, a marble and a feather have very different behavior. You drop a marble, it falls down directly, a feather takes its own sweet time. And to me, that's a great thing. So I want to go back to the era before Newton, before Galileo. Okay. So use the experimental observations of people, which essentially could be lots and lots of video. But, okay, and of course I remind you that this concept of mental model is an old one. How can we operationalize it with all these new tools that we have? So, this connects up to robotics, right? We have to have a model of an agent, and we have to have a model of an environment. And how do we act? How will the environment look in the future when the agent interacts with it? That's what we want to do. Okay, so let's do some case studies. So here's a simple example: billiards. You want to learn to play billiards. So you are going to apply a force and then do the right thing. So this is a setting where the model is actually known. I mean, this is Newtonian physics. It's totally understood. But what we did was we used this as a case study to understand how learning might enable us to understand physical models. So we need a model of the environment and a model of the agent. And this was a paper like last year at IECLA. And so what do? So we imagine that we have these moving ball worlds, and so you have various kinds of geometries, various number of balls, etc., etc. And what we want to do is to build a prediction module. So what this prediction module says is, suppose there is a certain configuration of the balls, and then you apply a certain force, what will happen next? Now this could be done totally by Newtonian physics, except that we are going to use learning approaches to acquire this prediction module. And okay, so then there are some details here, which is that you construct the model around objects, and as usual, you have some series of frames, you have ConvNet, some LSTM, etc., etc. So all this is published. So then in the model now has acquired this predictive model, and so the model's imagination, you can run it in the forward direction. So if you want to think of it in control theory, x dot equals ax plus bu, we can kind of do the prediction. and you can do this with multiple objects, etc. So what we did was we used Newtonian physics as a simulators to generate the training data for this learning architecture. And the idea is that this learning architecture will apply in other settings. And these are kind of the tracks that you get. So you can predict trajectories. And okay, so just some numbers to verify that this does reasonably. So now that we have learned predictive models, we can plan actions. And so this is going back to Kenneth Craig. You don't have to perform the action. You can imagine in your head what will happen if I apply a force going northwards, if I apply a force which is going northeast, etc., etc. And then you choose the optimal force. And this is important. This is because in real life you can't perform the action. This can be very dangerous. So you have to simulate the results of various actions. And it does reasonable things. Okay, but this one a very legitimate criticism is, okay, you've thrown this into learning mumbo jumbo, but it could have been done by classical physics. Now let's look at this example. So the question here is, who will possess the ball next? So this is a game of water polo and this player has the ball. And when the ball is in the air, this is a problem of Newtonian physics, right? Gravity takes over, there is some initial velocity, there will be a parabolic path. But I am asking the question of which of these players, whom will this player pass it to? Right? You might have some heuristics like, okay, the player nearest to the goal or the player who is not marked by another player, etc., etc. But learning can deal with this equally well. The prediction of the behavior of the ball and the prediction of the behavior of the player can be handled by exactly the same kind of machinery. So that is what makes it attractive to throw things into the learning framework. So this is why I said earlier that geometry, we have had to put it into the language of learning. And I think that here again we have classical physics, but we have to put it into the language of we have dynamics that we are going to learn. And so we have done stuff like this. So this person has the ball, whom can he pass it to? And now you can try to solve this problem. And you can do a learning approach. Again, I'm not going to use networks, etc., etc. And we can do reasonably well. The algorithm in trying to predict who will get the ball does as well as sort of people who are not domain experts. The people who are domain experts in water polo, they use much more subtle cues and can do better than the algorithm. But again, I'll skip the details. Okay, so here's so this was one of these examples was in simulation, which was the billiards example, and then there was this example of understanding the behavior of players, which in fact the techniques we have developed are quite general and they could apply to water polo or basketball or what have you, and we have in fact done that. Now let's apply it in a robotic setting. And so this is a paper which was presented at NIPS, and let me try to show this demo. So this tries to come close to this model of, remember this, I showed you these examples of how children learn by just poking around, grasping things, reaching out for things and so on. So here what we do is we have our robot be like the child. So what the robot does is there is some initial configuration of these objects. It pushes in a certain direction. There is an initial and final configuration which is captured by the image, and you just collect the data from like thousands of these pokes. Okay, and now so what's the input? So we basically have an initial and final configuration. So the robot applied some poke in a certain direction with a certain force. There was some initial image, so you acquire an image, and then there is an image after that has been applied, and then we want to sort of use this training data. So that's the training data. So the robot has done these 50,000 experiments, and from this we want to build this dynamical model which we then want to use for planning. So in fact we have to talk about two models here. There's an inverse model and the forward model. So the inverse model is there is some initial configuration, there is some desired final configuration. You want to run them through a network and figure out what force to apply. So that's the task. If you are doing planning, that's what you want to do. You want to predict what what action to apply. Then if you wanted to just in the eye's imagination figure out what will happen next when you apply the force, then we are in this forward model situation. There's an initial input, which is the image. There's some action that you apply, and then you want to predict this as output. But prediction in the pixel space is hard, because predicting pixels is hard. But we know that these two models together are what we want to do. And of course, there's a relationship between these models, the inverse model and the forward model. And so we want to jointly learn both the forward and inverse model. Again, all the details are in the inverse in the NIPS paper. And here's kind of the insight. So what we do is we take the images, we run them through convolutional nets. The weights are tied. So this is a Siamese architecture. There is the action itself, which is run through another network. And what you are trying to do is you construct this loss function based on the prediction. So in fact, you try to not predict the image, but you really try to predict the poke. You try to predict the poke, but you know what poke you did because you performed the action. And so you can now get a loss function there. You have the difference between the predicted poke and the actual poke, and you use that as a loss function, which you then differentiate, and you get a gradient to use to change the weights. So that's sort of the general idea. And then you can now do the quantification of this. How good is the forward model? How good is the inverse model? In fact, the way is it good for how well does it generalize? Can you perform a sequence of steps and so forth? And again, the details are in the NIPS paper. But I think of these as the big picture is really that these are all case studies of trying to learn by experimentation or by self-supervision. I don't know what's the right catchy term to use for this style of work. Calling it unsupervised learning somehow seems to miss essential aspects of this. And of course, we are not the only people to do this. Abhinav Gupta's group at CMU has been doing this for grasping. Sergey Levin has shown how to do this at large scale. And I expect that this kind of work will catch on. And this is showing that it's not just vision. There is vision and robotics. But I think we are at the point now where just staying in the world of vision alone is no longer the right thing to do. We really should couple to motor control and language. There's been a lot of work in the vision-language interface these days. And I'm arguing that the vision-robotics interface is equally important. And in fact, maybe it should come first, because if we believe in the notion of embodied cognition. Thank you very much. Right, so generalization, right? That's the question here. And I think we have some experimental evidence of that. And I think Abhinav Gupta's group has also done this. And I don't, again, have a generic answer to this. To me, it seems like, it's the usual problem of in learning, there's this general assumption that the distribution is the same in different settings, and that assumption is often not true. I generally think that the secret has to be doing lots and lots of tasks. So we want to not build idiosamas, right? We want to build these machines which are good for more than one thing. And as we try to have richer, so in vision, we have got great success at interpreting a patch of pixels as, is this a chair or a dog? We can do this really well. Okay, but there we are trying to push towards this kind of understanding of the world as having arisen from a 3D world. Okay, and then simultaneously here we are trying to understand dynamics of objects. And my feeling is that as we get to a richer and richer set of tasks, then trying to cheat will become harder and harder for the neural network. And at some point, okay, it may not be really understanding the world, but who the hell cares, right? If somebody insists that you must provide an explanation, what we would do is you run this model and then you have train a separate decision tree which emulates this, and then the public who wants an explanation can look at the output of the decision tree. Yes, it has some top level similarity. I mean, we didn't get to it from that reasoning. I mean, I think these ideas of having forward and inverse models really go back to sort of control theory and so forth. So it's a really much older. There's a much older literature to connect to, not just GANs. I mean, there are papers from Mike Jordan in the mid '80s on forward and inverse models in motor control. No, we haven't.